This video is supported by the National Science Foundation.
Hi, this is David Kobler. I'm here to present to you the next segment of our set of modules. In this section, we will discuss the integration of knowledge obtained from ICs and SEMs to create reverse engineering. Yes, we are going to be working on IC reverse engineering using SEM. I can't wait to take you through the process of combining knowledge from the two previous modules to really understand what reverse engineering is. In this module, we will explore the various steps of reverse engineering, paying attention to the important processes like deprocessing, which helps break down complex layers for better understanding. We'll also talk about why SEM is helpful in these procedures, highlighting its benefits. Additionally, we'll take a look at the key imaging details important in SEM. And then we'll also discuss how the beam intensity affects SEM. This detailed exploration will give you a step-by-step process allowing you to understand the reverse engineering using SEM on ICs. So let's answer the question, what is reverse engineering? In simple terms, reverse engineering is simply about understanding how a device is built and what it does. It involves dissecting the device and identifying the various components, like what we try to do with the ICs. In ICs, we focus on transistors and interconnections that come together to create the single unit we discussed in the previous lectures. Reverse engineering is a very time-consuming process. It could take days or even weeks depending on available resources. So the question is, why invest this much effort into this process? Well, we need a reliable method to compare designs to make sure that IPs are not infringed. IPs would be intellectual property. Device manufacturers want to make sure that their devices aren't being copied illegally and allowed to penetrate the market. It affects their profits and may also result in bad devices which aren't as functionally reliable as the original ones entering the market. Another reason why we use reverse engineering is to replace older ICs in entire systems. This is a very crucial role of reverse engineering where we address a concept called hardware obsolescence. In the cases where redesigning an entire system is impractical, especially for long-standing ones like in military and aerospace applications, reverse engineering becomes very essential. It allows us to examine and reproduce the ICs, enabling replacement of outdated components and keeping entire systems operational without overhauling them completely. With the knowledge of reverse engineering, let's try to understand its entire workflow. Let's go straight to the reverse engineering workflow. This is the entire reverse engineering workflow, and it kicks off with the target device. This is the device we want to figure out, and we can get our hands on it either by extracting it from a system or getting it from an outside source. So the first step for actual reverse engineering is the decapsulation process. This is the removal of the IC package, which is very much like unwrapping a gift. Doing this exposes the die and all its connections. Think of the die as the actual brains of the IC, and that holds all the important parts like the transistor, the wiring, and the interconnects. These are the components that come together to really help us understand how the device works. The next step on the journey of reverse engineering is deprocessing. This involves the careful removal of material from the IC to uncover its layers one by one. Now, the problem with that is it can change the IC completely. In fact, the reverse engineering process is obviously destructive. But don't worry too much. There are non destructive methods of IC reverse engineering. But for now, we focus on the destructive methods. Deprocessing itself has to delve into several layers of the IC. Every one of these layers has to be exhaustively imaged during the process. Starting from the front side, which is the top of the IC, we go to the diffusion layer. This layer is very important because it has the distribution of certain materials that contribute to the overall performance of the IC. We also see the polysilicon layer, which is a form of silicon, and is used to create the conductive parts and the structures within the IC. It is very essential for the functionality and connectivity of the device. The next ones are the contact layers that facilitate the connections between the different parts of the IC, ensuring that signals can flow smoothly. They are the bridges that allow information to travel within the IC. Finally, the metal layers are available that carry signals within the IC. They are the highways that allow us to conduct electronic signals for the overall operation of the IC. Like I said before, the deprocessing step involves constantly taking images of layers as we work our way through. By doing so, we get a very detailed visual representation of the device that can be used for the reverse engineering process moving forward. Now that we know deprocessing and how many layers we need to interact with to get a detailed deprocessing step, let's delve into the imaging aspect of it. As we go back to our engineering workflow, let's focus on imaging. We are about to revisit the SEM we learned in the previous presentation. Why do we choose SEM? I'm going to tell you why. One standout feature is its extensive range of magnification. Think about the camera that your iPhone provides. With its humble 3 to 4 times magnification, the SEM can go all the way up to 142 times, but that is not its ceiling. You can obtain as much as 45,000 times magnification using the SEM, and this allows us to identify minuscule components such as the tiny bits of transistor you can see on the right-hand image. These kind of images are only visible when you can use an SEM. Another reason we use the SEM is its high depth of focus. Consider the formations on the left side. These are at a depth of 2200 times. Even at this depth, you can see a clear view, allowing us to really distinguish the individual structures. What's truly remarkable about the SEM is it can go all the way to 100,000 times while still maintaining focus, allowing us to precisely distinguish individual structures. This is very valuable during the reverse engineering process and allows us to examine devices at a very precise level. Now let's talk about the SEM imaging parameters. Certain factors such as dwelling time are really vital for obtaining accurate results. Dwelling time is simply the amount of time the scanning beam takes to measure the intensity of a pixel. It's a very technical detail and it's very important for achieving precise focus. As you can see, the difference between 3.2 microseconds per pixel and 32 microseconds per pixel. Additionally, precise magnification is very essential. Optimal focus is obtained with specific magnification settings, such as comparing the 20 by 20 micrometer to the 500 by 500 micrometer you can see on the middle images. Similarly, resolution plays a very important role when capturing detailed images. The higher resolution is very necessary to actually find intricate structures and positions. During the SEM process, all these parameters combine to get a very precise reverse engineering image. All these images are adjustable. They are not automatically obtained. The expert user will have to go through several trials and errors to make sure that they get the best settings for their specific device. After successful deprocessing and imaging, we can annotate our images. The annotation is like drawing a map where we outline the most important features. We're able to highlight the settings and connections that make the device function. We are able to really understand its structure and we're able to put together its positions within the entire IC. Moving on, we can perform netlist extraction after the annotation. In this method, we are able to make graph-like connections of the various components of the IC. This becomes the blueprint of the different elements in the device that we can use to understand its structure and especially its functionality. The netlist process allows us to even extract the standard cells that have been used to create the IC. The standard cells, for example, would be the gate that I described as a single unit in the IC module 2 presentations earlier. Once we understand the workings of the device with the netlist and the annotations, you are able to create your fully reverse engineered device and use it to assess or perform hardware obsolescence replacement. This is the conclusion of our work on IC reverse engineering using SEM. Thank you for joining me, and I look forward to seeing you in subsequent modules in the future.